What if everything, every star, every galaxy, every atom in your body came from nothing, not just empty space, but absolute nothingness? No matter, no energy, no time. And yet, here we are, in a universe bursting with complexity, stretching for billions of light years in all directions. How does something emerge from nothing? Has the universe always existed in some form?
For decades, scientists have tried to piece this puzzle together. Was our universe born from a quantum fluctuation? Did an earlier cosmos collapse and explode into a new cycle of existence? Let's dive into the strangest, most mind-bending theories of the universe's origins. If you think the Big Bang is the final answer, think again. The truth might be far weirder than you imagined. From ancient times to modern physics, our understanding of nothing has undergone a complete transformation. What once seemed like an empty void has become something far more complex. In ancient Greece, philosophers like Aristotle rejected the idea that true emptiness could exist. To him, nature abhorred a vacuum. He believed space must always be filled with something: air, fire, or some other invisible substance. This idea dominated scientific thought for centuries.
The 17th century brought a turning point. The work of Galileo and later Newton helped shape a new understanding of space. Newton described space as an absolute void, a background in which objects moved according to predictable laws. Space itself, he thought, had no structure. It was simply a stage on which the universe played out. However, even in Newton's time, some scientists suspected that space might not be entirely empty.
In the 19th century, scientists proposed the existence of an invisible medium called the ether. This ether was thought to fill all of space and serve as the carrier of light waves. Since sound needed air to travel, scientists assumed light also needed a medium. The idea fit well with Newtonian physics. However, in the late 1800s, the famous Michelson-Morley experiment attempted to detect the motion of the ether by measuring how light moved through space. The results showed no sign of the ether's existence, posing a major problem for physics. At the turn of the 20th century, Einstein's theory of relativity offered a revolutionary view. Space was no longer seen as a passive void, but as a dynamic fabric that could stretch and bend. Gravity was reimagined, not as a force pulling objects together, but as the result of massive objects warping the structure of space itself. This view marked a significant shift from the classical void. But the most dramatic transformation came with the rise of quantum mechanics. This new science showed that even in a vacuum, particles could pop in and out of existence, so-called virtual particles, appearing and disappearing so quickly they couldn't be directly observed. This constant activity gave rise to the concept of the quantum vacuum. Instead of being empty, space was filled with fluctuations, tiny bursts of energy happening everywhere all the time. The vacuum was no longer just an absence of matter. It was an active participant in the universe. The Casimir effect, first proposed in 1948, showed that two closely placed metal plates could experience an attractive force due to quantum vacuum fluctuations, solid evidence that the vacuum had real physical properties. In quantum field theory, every type of particle has a corresponding field spread throughout space. Even when no particles are present, these fields continue to exist, constantly fluctuating. The Higgs field, for example, gives particles their mass. Without it, the fundamental particles that make up matter wouldn't exist in their familiar form. This understanding of empty space reshaped cosmology. The discovery of dark energy, the mysterious force causing the universe's expansion to accelerate, is closely linked to the quantum vacuum. Some scientists believe that vacuum energy, arising from quantum fluctuations, may be responsible for this cosmic acceleration. Yet, the exact nature of dark energy remains one of the greatest mysteries in physics. The journey from the classical void to the quantum vacuum marks a major shift in scientific thought. What was once considered nothing is now seen as a source of energy and activity. Scientists continue to explore this mystery. Could vacuum energy be harnessed? Could new physics be hiding in the structure of empty space? The answers to these questions could reshape our understanding of the cosmos.
In classical physics, a vacuum is simply an absence of matter. But in quantum physics, even empty space contains energy in the form of short-lived virtual particles that emerge and vanish before they can be directly observed. Yet, their effects can be measured, proving they are real.
The Big Bang, which started everything, is often described as a massive explosion. But what triggered it? One possibility is a quantum fluctuation arising from an unstable state of empty space. At an incredibly small scale, the universe may have begun as a tiny fluctuation in a quantum vacuum. Normally, such fluctuations are brief, but under certain conditions, a fluctuation could become stable and expand rapidly.
This idea is tied to inflation, the theory that the early universe expanded at an extraordinary rate. Inflation suggests that in a fraction of a second, the universe grew from an unimaginably small size to something vast. If a quantum fluctuation triggered this expansion, it would mean that the universe itself emerged from the hidden energy of empty space.
If one quantum fluctuation could create a universe, could others do the same? Some scientists believe fluctuations like this might happen all the time, producing countless universes beyond our own. This idea, known as eternal inflation, suggests that new regions of space are constantly forming in an ever-expanding cosmic landscape.
Even within our own universe, quantum fluctuations left their mark. As inflation stretched space, tiny fluctuations were magnified. These small differences in energy density became the seeds of galaxies and stars. Without them, matter might have remained evenly spread, never clumping into the cosmic structures we see today.
The idea that the universe could emerge from nothing may seem strange, but experiments confirm that quantum fluctuations are real and have measurable effects. In particle physics, they influence the behavior of fundamental forces and particles. If they shaped the universe on the smallest scale, they may have influenced it on the largest scale too.
Vacuum energy isn't just a backdrop. It can shift from one state to another. In some theories, if an unstable vacuum state existed before the Big Bang, a quantum fluctuation could have triggered a transition leading to the birth of the cosmos. If a quantum event started our universe, could other universes be forming right now? Could new universes emerge in the distant future? These possibilities arise naturally from the strange rules of quantum physics.
The Big Bang is the foundation of modern cosmology, the event that marks the start of the observable universe. But what if it wasn't the true beginning? For decades, physicists and cosmologists have explored the idea that the universe had a history before the Big Bang.
Some theories suggest that the cosmos has gone through endless cycles of expansion and contraction, never truly beginning or ending. Others propose that our universe was born from a much larger pre-existing reality, possibly through interactions between hidden dimensions or unknown physical forces.
If these ideas are correct, the Big Bang was not the beginning, but just one event in a much older and larger cosmic story. One of the most discussed alternatives is the cyclic universe model. This theory suggests that the universe follows a repeating pattern, expanding, slowing down, contracting, and starting over again.
Instead of a single Big Bang followed by endless expansion, the cosmos could go through an infinite series of big bangs and big crunches. Ancient cultures, including Hindu and Buddhist traditions, imagined the universe as undergoing endless cycles of creation and destruction. In modern physics, this concept has been explored in various forms. Some versions propose that dark energy might one day reverse, pulling everything back together. The universe would shrink down to an incredibly dense state before bouncing back in another explosion. This process, repeated infinitely, could mean that the universe has no true beginning or end, only endless rebirth. A variation of this idea is the Big Bounce theory. It suggests that rather than collapsing into a singularity, a previous universe reached a highly compressed state and then rebounded, creating our current expanding universe. In classical physics, gravity would eventually pull everything back into a single point, creating a singularity. But in quantum mechanics, effects at the smallest scales could prevent this total collapse. Instead of a singularity, a new expansion could begin, leading to a fresh universe. Some versions of this theory suggest that each new universe might carry imprints from the previous one, tiny differences that could be reflected in the cosmic microwave background. String theory proposes that the fundamental building blocks of reality are tiny vibrating strings rather than point-like particles. In one version of string theory, called the ikpyrotic model, the universe was formed not by a singular explosion, but by a collision between two enormous, higher dimensional surfaces known as branes. According to this idea, space could have more than the 3 dimensions we experience, and these higher dimensional structures could interact in ways that create entire universes. In that case, the Big Bang would not be a unique event. It would be just one of many such collisions occurring across an unimaginably vast cosmic landscape. Another possibility is that the universe emerged from quantum fluctuations in an eternal vacuum. If a fluctuation occurred under the right conditions, it could have triggered rapid inflation, leading to the birth of our universe. This idea suggests that our universe is just one bubble in a much larger quantum reality, constantly giving rise to new universes. This leads to the idea of the multiverse, a vast collection of universes, each with its own unique properties. Some versions of the multiverse theory propose that every quantum event spawns a new universe, creating an endless number of parallel realities. Others suggest that different regions of space are constantly producing new universes, separated from one another by immense distances or even by different dimensions. If true, this would mean our universe is just one of countless others, each with its own physical laws, matter, and possibilities. Some theories suggest that instead of starting at a single moment, time could stretch infinitely into the past. In this view, what we see as the Big Bang might simply be a transition from one phase of existence to another. One way to explore these ideas is through mathematical models and observations of the cosmic microwave background radiation, or CMB. This faint glow left over from the early universe carries clues about what happened in the first moments after the Big Bang. Some scientists believe that subtle patterns in this radiation could reveal hints about a pre-existing universe. If traces of an earlier phase of the cosmos were found, it would be a major breakthrough in our understanding of cosmic history. Since the laws of physics, as we know them, break down under the extreme conditions of the early universe, it is difficult to gather direct evidence about anything that might have come before. Many of these ideas, while based on solid theoretical foundations, remain speculative because they cannot yet be tested. However, advances in physics and technology may one day provide new insights. As scientists develop more precise instruments and explore deeper questions about the nature of space, time, and matter, they may uncover clues that point to a time before the Big Bang. Quantum gravity plays a central role in the question of cosmic genesis. The universe follows two sets of rules that seem completely different. One set governs how planets, stars, and galaxies behave, following the familiar laws of gravity first described by Isaac Newton and later expanded by Albert Einstein. The other set governs the strange world of the very small atoms, particles, and the energy fields that surround them, described by quantum mechanics. Both theories have been tested and confirmed in countless experiments, yet they seem impossible to combine. This is a major problem because to truly understand the birth of the universe, both gravity and quantum mechanics must be considered together. At the moment of the Big Bang, the entire universe was packed into an unimaginably small space. This means gravity was acting at the quantum scale, where the rules of quantum mechanics take over. But Einstein's theory of general relativity, which explains gravity on large scales, does not work at the quantum level. Similarly, quantum mechanics, which describes small-scale physics, does not include gravity. The two theories break down when combined, leaving physicists without a complete explanation for the earliest moments of the universe. To understand cosmic origins, scientists must develop a theory that merges these two fundamental forces into one unified framework. One approach to solving this mystery is the search for quantum gravity, a theory that explains how gravity works in the quantum world. This is considered one of the biggest unsolved problems in physics. If a theory of quantum gravity is found, it could reveal what happened in the first instant of the universe, possibly even before the Big Bang itself. One of the leading ideas in quantum gravity is string theory. Instead of treating particles as single points, string theory suggests that everything is made up of tiny vibrating strings. These strings are so small, they would be impossible to see, even with the most powerful microscope. Depending on how they vibrate, these strings could represent different forces and particles, including gravity. In this view, gravity is not a separate force, but an effect of these vibrating strings interacting with space. String theory also suggests that space may have more than 3 dimensions. While we experience height, width, and depth in our everyday world, extra dimensions could exist hidden from view. If true, the early universe may have behaved very differently than we expect. These extra dimensions could have influenced how space expanded after the Big Bang, or even played a role in how the universe came into existence in the first place.
A different approach to quantum gravity is loop quantum gravity. Instead of treating space as a smooth background, this theory suggests that space itself is made of tiny, indivisible units, much like pixels on a screen. These quantized bits of space create a structure that could prevent the universe from collapsing into a singularity. This could explain how the universe transitioned from a previous state into the one we see today. Some versions of loop quantum gravity suggest that time itself might be fundamentally different at the quantum level. Rather than flowing smoothly, time may emerge from deeper interactions within the fabric of space. This could mean that time existed before the Big Bang, allowing for a history that stretches back beyond the beginning we currently recognize.
A third idea comes from the holographic principle. This concept suggests that the entire universe may be like a 3-dimensional projection of information stored on a distant, lower-dimensional surface. In this view, the universe's deepest structure is not made of physical matter, but of information itself. If the holographic principle is correct, the birth of the universe might not have been a traditional explosion, but rather the emergence of information forming space and time.
One of the biggest challenges in developing a theory of quantum gravity is testing it. Unlike other areas of physics, where experiments can be done in labs or with telescopes, the conditions needed to study quantum gravity directly would require recreating the extreme environment of the early universe. Since that's impossible with current technology, physicists must look for indirect clues, subtle patterns in the CMB, the behavior of black holes, or strange effects in high-energy particle experiments. Black holes are similar in some ways to the conditions of the early universe. Stephen Hawking famously predicted that black holes slowly lose energy over time through a process now called Hawking radiation. This happens because quantum effects near the black hole's edge cause particles to pop into existence and escape. If quantum gravity plays a role in black holes, studying their evaporation could provide insights into the universe's first moments. The CMB holds information about the early universe, and small irregularities in it could reveal whether quantum gravity had an effect during the first fractions of a second. If patterns appear that don't fit with standard cosmology, they could point to new physics beyond Einstein's equations.
There is also the question of whether the universe needed a beginning at all. Some theories of quantum gravity suggest that time itself may behave differently under extreme conditions. If time and space emerge from quantum interactions, then the Big Bang might not have been a singular event, but rather a transition from one state to another. The universe may have always existed in some form, with no absolute beginning, only changes in its structure over time.
If scientists succeed in merging quantum mechanics and gravity into a single framework, it could lead to entirely new ways of thinking about space, time, and the universe's structure. It might even provide the foundation for new technologies or discoveries. Scientists push forward, driven by the need to understand the fundamental nature of everything that exists.
Emergence of space-time, when geometry is born.
Before the birth of the universe as we know it, there may have been no space and no time, at least not in the way we understand these things. The fabric of reality itself might not be fundamental. Instead, it may have emerged from deeper processes that have nothing to do with the familiar ideas of space stretching infinitely or time flowing smoothly. One way to think about this is to compare space-time to temperature. Temperature feels like a basic property of the world, but in reality it is just the collective motion of microscopic particles.
Of individual atoms, the idea of temperature disappears. It is not something that exists on its own, but something that emerges from the behavior of many smaller pieces interacting. Some physicists believe space and time might work the same way. On the smallest scales, they may not exist at all, appearing only when enough interactions take place to give them meaning.
In the quantum world, particles do not always have fixed locations. Their positions can be uncertain, and sometimes they exist in multiple states at once. If space itself is something that emerges, then at the smallest scales, locations may not exist in a definite way. Reality could be made of interconnected relationships, with space forming only when enough connections stabilize.
Some theories propose that the fundamental structure of reality is not based on space at all, but on networks of information. In these views, space is not a physical thing, but a way of organizing relationships between tiny building blocks. These networks behave in a way that at large scales creates the smooth geometry of space that we experience. Just as individual grains of sand can form a solid beach, individual pieces of information could form the structure of space-time.
One model based on this idea is known as causal set theory. In this view, space-time is not a continuous fabric, but a collection of discrete elements, like dots connected by cause and effect relationships. Instead of existing as a background, space-time is built from these connections, appearing smooth only at large scales. If causal set theory is correct, then at the smallest levels, space does not exist in the way we normally think. It is not an empty container, but something that emerges when enough interactions occur.
Another approach comes from loop quantum gravity. Just as energy comes in discrete packets called quanta, space may be divided into tiny indivisible units known as loops. These loops form a kind of network that underlies the structure of space-time. At small scales, space is woven together like a fabric made of interlocking loops. This would mean that space itself has the smallest possible unit, beyond which the idea of distance no longer makes sense.
If space is made up of fundamental units, then time might be as well. Some physicists propose that time is not a continuous flow, but a sequence of discrete events, like frames in a film. At the quantum level, there may be a fundamental tick of time. This idea is supported by certain interpretations of quantum mechanics, which suggest that time emerges from changes in quantum states, rather than existing independently.
One of the biggest implications of these ideas is that the Big Bang may not have been the beginning of space and time, but rather the moment when they emerged from a deeper, more fundamental reality. If space-time itself had to form, then there could have been a stage before the Big Bang where space did not exist in any recognizable form. Instead of a single explosive event, the universe may have transitioned from a timeless quantum state into the dynamic, expanding cosmos we see today.
Scientists are searching for evidence of these ideas in various ways. If space formed from deeper processes, then small imprints might still be visible in the oldest light in the universe. The extreme warping of space and time by black holes could also reveal how space-time behaves when pushed to its limits. If space-time is something that emerges rather than something that exists on its own, what lies beyond space-time? What deeper principles determine its structure? And if space and time are not fundamental, what does that mean for our understanding of existence itself? Multiverse narratives explore the idea of multiple beginnings from nothing. The cosmos, rather than being a single expanding bubble, could be a vast multiverse filled with countless separate regions, each with its own laws, structures, and origins. If this is true, then instead of asking how everything began, we might have to ask how many different ways something can emerge from what we call nothing. According to eternal inflation, space itself is constantly expanding at an incredible rate in most regions. But in certain pockets, the rapid expansion slows down. These slower regions become bubble universes, each forming with its own unique properties. Our universe could be one of these bubbles, surrounded by an endless cosmic foam of other universes. If eternal inflation is correct, then new universes could be forming all the time. The process never stops. Each bubble universe emerges from a quantum fluctuation, a random energy shift in the vacuum of space. This means that, rather than a single Big Bang event, the cosmos could be filled with countless Big Bangs, each creating a separate universe. Some of these universes might have similar physical laws to ours, while others could be completely unrecognizable, governed by different rules of physics that make them alien and strange.
In string theory, the way the strings vibrate determines the properties of a universe, its particles, forces, and dimensions. But string theory predicts that there are an immense number of ways these strings could be arranged. Some estimates suggest there could be around 10,500 possible configurations, each corresponding to a different universe with different physical properties.
In some versions of the multiverse, universes can even branch off from one another. The many worlds interpretation of quantum mechanics suggests that every quantum event, every tiny random change in a particle's state, could cause the universe to split. If this interpretation is correct, then an uncountable number of parallel universes could exist, each representing a different version of reality. Every decision, every movement of an atom could lead to a separate world where things unfold differently. If black holes are gateways to new regions of space, then each black hole in our universe could potentially give rise to a new universe beyond its event horizon. This would mean that our own universe might have formed from the remains of a previous one, continuing a never-ending cycle of cosmic creation.
While the multiverse remains a highly speculative idea, scientists continue searching for ways to test it. Some look for evidence in the cosmic microwave background, CMB. Others search for signs of extra dimensions or variations in fundamental constants that could hint at a deeper underlying reality.
Vacuum energy and the sea of possibility also play a role in these grand ideas. Vacuum energy comes from the fundamental nature of quantum fields. Even in a space with no particles, these fields are never completely at rest. They continue to vibrate at a fundamental level, producing short-lived bursts of energy. These fluctuations are normally small, appearing and vanishing too quickly to have a noticeable effect. However, under the right conditions, they could play a much larger role, potentially giving rise to entire universes.
The concept of vacuum energy also connects to one of the biggest puzzles in physics, the cosmological constant. When Albert Einstein developed his equations of general relativity, he included a term called the cosmological constant to describe the energy of empty space. At the time, it was thought to be a mathematical adjustment, but later discoveries revealed that vacuum energy is real and has an observable effect on the universe.
Today, the cosmological constant is linked to dark energy.
The amount of vacuum energy in the universe appears to be incredibly small compared to theoretical predictions. If the calculations based on quantum field theory were correct, the energy of empty space should be strong enough to tear apart galaxies instantly. Instead, the observed value is much weaker, suggesting either that we are missing a key part of the picture or that there is an unknown mechanism balancing vacuum energy at just the right level for our universe to exist. If vacuum energy plays a role in creating new universes, then different regions of the multiverse could have different values for this energy. Some universes might have a much stronger vacuum energy, causing space to expand so quickly that stars and galaxies never form. Others might have almost no vacuum energy, leading to a universe that collapses in on itself shortly after forming. The fact that our universe has a vacuum energy compatible with life could be a clue that many universes exist, each with different physical properties. If space itself contains energy, then in theory, it might be possible to extract or alter this energy. This idea appears in discussions about advanced propulsion systems, where the manipulation of vacuum energy could one day allow faster-than-light travel. While purely speculative, the possibility of tapping into the energy of empty space remains an intriguing subject of exploration. The effects of this energy can be seen in experiments such as with the Casimir effect, demonstrating that vacuum energy is not just a theoretical concept, but something that can influence physical objects in measurable ways.
If vacuum energy is the driving force behind cosmic creation, then the birth of universes may not require an external cause. Instead, the natural fluctuations of the vacuum could be enough to trigger the formation of entire cosmic structures.
Entropy is a fundamental part of how the universe works. It is the measure of disorder, and according to the second law of thermodynamics, entropy always increases over time. Left alone, systems tend to move from order to disorder. A shattered glass never reassembles itself, and a drop of ink in water spreads out rather than gathering back into a single spot.
Yet, when we look at the early universe, we find something unexpected. It began in an incredibly low entropy state, highly ordered compared to what came after. If entropy naturally increases, why was the universe so ordered at the beginning?
When the universe first emerged from the Big Bang, it was in a hot, dense state. Matter and energy were evenly spread, with only tiny variations. This seems like a simple and chaotic state. Yet in terms of entropy, it was remarkably low. Over time, the universe expanded, cooled, and formed complex structures, like galaxies, stars, and planets. Eventually, these structures will break down, and everything will drift toward a state of maximum entropy, where matter and energy are spread out so evenly
but no useful work can be done. This final state, often called the heat death of the universe, represents ultimate disorder.
The puzzle is why the universe started in a condition that allowed all of this structure to form. If high entropy is the natural end state, then why didn't the universe begin in a high entropy state from the start? Why was there order that gave rise to stars and galaxies instead of an immediate collapse into randomness?
One way to understand the problem is to think about gravity. In most systems, an increase in entropy means things become more spread out. But gravity behaves differently. When a cloud of gas collapses into a star, it seems to be getting more ordered rather than more disordered. This happens because gravity pulls matter together, forming dense structures. Yet, in doing so, it actually increases the overall entropy of the universe by releasing heat and radiation. The process of structure formation is not a decrease in entropy, but rather a distribution of it.
Some physicists propose that the universe's initial state wasn't just low entropy, but also highly specific. In order for space and time to emerge as we know them, the initial conditions had to be just right, almost as if the universe began in a state of special fine-tuning. This is sometimes referred to as the past hypothesis, the idea that the early universe was simply in a unique condition that set the stage for everything that followed.
While inflation can explain why the universe appears so uniform on large scales, it doesn't fully answer why entropy started out so low. The deeper question remains, why did inflation itself occur in the first place, and why was its starting conditions so special?
In the cyclic model view, the Big Bang is just one stage of a much longer history. If the universe collapses and then expands again, the conditions at each new beginning might be reset in a way that keeps entropy low. However, this idea raises its own challenges, such as explaining how entropy resets with each cycle instead of building up indefinitely.
If the multiverse exists, then perhaps we live in a universe that just happened to begin with low entropy. In this case, our universe is one of many possibilities, and we observe a low entropy beginning simply because we exist in a universe where conditions allowed complex structures like galaxies and life to form. If our universe had started with high entropy, it might have been too chaotic for stars and planets to develop, and observers like us would not be here to ask these questions.
This entropy paradox is not just a puzzle about the past, it affects how we think about the future. As entropy continues to increase, the universe will eventually reach a state where no further work can be done, where stars burn out, black holes evaporate, and all matter is evenly spread across an expanding void. But if the universe can begin again, or if new regions of space can emerge from vacuum fluctuations, then perhaps entropy is not the final word. Instead, the cycle of order and disorder may continue, driven by even deeper processes.
Revisiting cosmic inflation beyond the standard picture.
The expansion associated with cosmic inflation smoothed out irregularities, making the cosmos look the way it does today. The theory explains why the universe appears so uniform in all directions, and why distant regions of space have similar properties, even though they should never have been in contact with each other. Inflation also accounts for the absence of certain defects in space-time. Early models of the Big Bang predicted that relics like magnetic monopoles, hypothetical particles with only one magnetic pole, should be common in the universe, yet none have been found. Inflation explains this by stretching space so much that any such relics would be extremely rare or pushed far beyond the observable universe.
These successes have made inflation a widely accepted part of cosmology, but the theory is not without its challenges. One of the biggest issues is that inflation relies on an unknown force. The rapid expansion is thought to have been driven by a mysterious field, sometimes called the inflaton field, which has no known counterpart in the standard model of particle physics. Scientists do not yet know what this field was or what kind of energy it carried. While many models propose possible explanations, there is no direct evidence for the exact nature of the inflaton, making inflation a theory that works well in explaining observations, but lacks a clear physical foundation.
There is also the problem of how inflation ended. According to the theory, the inflaton field eventually decayed, transferring its energy into the particles and radiation that would go on to form the universe. But the process by which this transition happened is still not fully understood. Some models suggest that inflation ended smoothly, while others propose that it may have triggered violent bursts of energy, creating high-density regions that influenced later cosmic structure.
These questions have led to alternative models, such as the eternal inflation model and the bouncing universe model, which go beyond the standard picture of inflation. Another approach involves modifying gravity itself. Some theories suggest that what we interpret as inflation could be the result of an unknown aspect of gravity that only appears at extremely high energies. These models propose that the fabric of space-time behaved differently in the earliest moments of the universe, making it naturally evolve into a smooth, uniform state without requiring an extra field like the inflation. If this is true, then inflation may be an approximation of a deeper, more fundamental process. Since certain models of string theory, inflation could be driven by the interactions between extra spatial dimensions, which are predicted by the theory but are too small to be observed directly. If these extra dimensions influence the early universe, they could provide an entirely new explanation for how inflation worked, or even suggest that something else entirely took its place.
Observational evidence is crucial for distinguishing between these competing ideas. One of the strongest pieces of evidence for inflation comes from the cosmic microwave background, CMB. Tiny variations in this radiation reveal patterns that match what inflation predicts. However, different models of inflation and even some alternative theories can produce similar patterns, making it difficult to determine which one is correct.
Scientists are looking for additional clues that could confirm or challenge inflation. One major goal is detecting primordial gravitational waves, ripples in space-time that could have been created by inflation. If found, these waves would provide strong support for the idea of a rapid expansion phase. Experiments using specialized telescopes to study the polarization of the CMB are searching for these signals. A confirmed detection would not only strengthen the case for inflation, but also help narrow down which version of the theory is correct. Another approach involves looking for signs of non-uniformity on the largest scales. While inflation is expected to have smoothed out the universe, some variations in structure could still be present depending on the specific details of how inflation happened. If these variations were found, they could provide hints about the nature of the inflaton field, or even suggest that inflation worked differently than currently believed. Primordial black holes, PBHs, are hypothetical black holes that may have formed in the early universe, long before stars and galaxies emerged. Unlike black holes, formed from stellar collapse, PBHs could originate from extreme density fluctuations shortly after the Big Bang. These fluctuations might have created regions where gravity was strong enough to cause collapse into black holes.
Although PBHs do not emit light, they can interact with normal matter through gravity. Even small PBHs can accrete gas and dust, heating it up and producing radiation detectable by telescopes. If a large number of PBHs existed, they could have emitted too much radiation early in cosmic history, altering the cosmic microwave background, CMB. Current CMB data has placed strict constraints on the possible number of PBHs.
However, PBHs might still contribute to dark matter, especially if they have a range of masses.
or unusual clustering behavior. Some theories propose that dark matter could include black hole remnants, tiny black holes that have evaporated via Hawking radiation. Others suggest that PBHAs might have served as the seeds for supermassive black holes found in galaxy centers. These early PBHAs could have merged and grown rapidly, bypassing the usual star collapse path.
Scientists also search for PBHs using gravitational lensing, where a black hole passing in front of a star temporarily magnifies its light. Additionally, the final stages of evaporation of small PBHs might produce brief gamma-ray bursts detectable by space telescopes. Unusual properties or exotic structures like wormholes may also be associated with PBHs, further motivating their study.
In terms of cosmic structure, PBHAs could have influenced how matter clustered in the early universe. Their gravitational effects might have accelerated the formation of galaxies and clusters by acting as early gravitational wells. The cosmic web, a large-scale structure of filaments and voids, could also bear the imprint of PBH activity. PBHAs may have enhanced or disrupted the formation of certain regions, altering the distribution of galaxies.
Gravitational wave observatories like LIGO and Virgo have detected black hole mergers that some believe could involve PBHs, especially when the observed black holes don't match known stellar evolution pathways. These observations may provide indirect evidence of PBHs.
The CMB offers a snapshot of the universe nearly 14 billion years ago and contains anomalies that may hint at new physics. One such anomaly is the cold spot, a region with lower than expected temperature, possibly linked to a supervoid or a collision with another universe in a multiverse scenario. Another is the axis of evil, an alignment of large-scale temperature fluctuations suggesting a preferred direction in the cosmos, challenging the assumption of isotropy.
Polarization in the CMB, particularly B-mode polarization, offers another avenue for probing the early universe. B-modes could be the result of primordial gravitational waves from inflation. While the 2014 BASEP-2 results sparked excitement, later analysis attributed the signal to galactic dust. Future missions like Lightbird aim to detect these subtle signals with greater precision.
Temperature fluctuations in the CMB also deviate slightly from predictions at the largest scales, suggesting that our understanding of inflation might need refinement. These subtle clues, whether in temperature, polarization, or gravitational waves, could unlock profound insights into the nature of space, time, and the origins of the universe.
Primordial black holes remain an enticing possibility, linking the physics of the Big Bang, dark matter, cosmic structure, and black hole formation into a single framework. Their discovery, if confirmed, would reshape our understanding of the universe.
Detecting the undetectable, techniques for observing primordial gravitational waves. Unlike the gravitational waves detected from black hole mergers, which produce ripples in space-time that can be observed with current instruments, primordial gravitational waves are far weaker. These waves, if they exist, would have been generated in the first fractions of a second after the Big Bang, stretching and squeezing space itself. Capturing such faint signals requires not just precise instruments, but entirely new ways of observing the cosmos.
As these waves traveled through the early universe, they would have left behind a subtle twisting pattern in the polarization of the cosmic microwave background, CMB. This B-mode polarization is one of the primary targets for experiments aiming to detect these ancient ripples in space-time. Unlike temperature fluctuations in the CMB, which have been studied in great detail, B-mode polarization is much harder to measure. It requires instruments with extreme sensitivity capable of distinguishing these weak signals from other sources of cosmic noise.
Ground-based telescopes, such as the South Pole Telescope and the Atacama Cosmology Telescope, are equipped with specialized detectors
to scan the sky for signs of B-mode polarization. These observatories are located in remote, high-altitude regions to minimize interference from Earth's atmosphere, which can distort microwave signals. Space-based missions offer another approach. NASA and the European Space Agency have proposed next-generation satellites designed specifically for this task, offering greater accuracy than ever before. Unlike ground-based telescopes, space-based instruments can avoid atmospheric interference entirely, providing a clearer and more precise view of the early universe.
Another technique for detecting these waves involves laser interferometry. However, the wavelengths of primordial gravitational waves are vastly longer, requiring interferometers on an unprecedented scale. The proposed LISA Laser Interferometer Space Antenna mission aims to deploy a trio of spacecraft in orbit around the Sun, forming a giant triangle millions of kilometers across. This setup would allow LISA to detect ultra-low frequency gravitational waves that ground-based detectors cannot observe. While LISA's primary mission is to study waves from supermassive black holes, it could also help place new constraints on the strength of primordial gravitational waves.
Pulsars timing arrays represent another innovative approach. Pulsars are rapidly spinning neutron stars that emit beams of radio waves with extraordinary precision. By monitoring the timing of these pulses across a network of pulsars distributed throughout the galaxy, astronomers can look for tiny deviations caused by passing gravitational waves. Although pulsar timing arrays are more suited for detecting waves from merging black holes, they could also reveal hints of primordial gravitational waves if the right conditions are met. Long-term monitoring of pulsars with next-generation radio telescopes such as the Square Kilometre Array could improve sensitivity to these faint signals.
Different models of cosmic inflation predict different strengths and patterns of gravitational waves, meaning that a successful detection could help determine which inflationary scenario best describes the early universe. Some theories even suggest that the absence of primordial gravitational waves at a certain level could rule out standard inflation entirely, pointing toward alternative explanations for the origin of the universe.
Quantum signatures in gravitational waveforms.
The gravitational waves detected so far have come from merging black holes or neutron stars, sending signals that match predictions made by Einstein's general relativity. But some scientists believe these waves might carry even more information, traces of quantum processes from the earliest moments of the universe.
One way quantum effects might appear in gravitational waves is through quantum fluctuations. In the early universe, space itself was filled with tiny, random energy fluctuations caused by quantum uncertainty. Normally, these fluctuations remain too small to detect, but during cosmic inflation, these quantum variations were stretched to much larger scales. Some of these fluctuations could have created ripples in space-time, forming gravitational waves with unique quantum signatures.
If such signals exist, they would look different from the gravitational waves produced by merging black holes or neutron stars. Standard gravitational waves have smooth, predictable waveforms that match the equations of general relativity. But quantum signatures could introduce tiny distortions or irregular patterns, subtle imprints that do not fit into classical physics. Some theories even predict that gravitational waves could carry entanglement, a strange quantum connection where two particles or even two regions of space-time remain linked no matter how far apart they are.
Detecting these quantum effects in gravitational waves would require instruments far more sensitive than those currently in use. Observatories like LIGO and Virgo are already capable of measuring incredibly small changes in space-time distortions, thousands of times smaller than an atom. But quantum signatures would be even fainter, possibly requiring new detection methods beyond current laser interferometers.
One possible approach involves studying the statistical properties of gravitational wave signals rather than just individual waveforms. If quantum effects are present, They might cause slight variations in the way waves are distributed over time or across different events. Some researchers have even proposed using quantum experiments on Earth to simulate aspects of gravitational waves. By creating controlled conditions where quantum particles interact with artificial gravitational fields, scientists could test whether certain quantum signatures appear. These experiments wouldn't replace real gravitational wave observations, but they could provide clues about what to look for in space.
If quantum signatures in gravitational waves are confirmed, it would suggest that gravity itself has a quantum nature, challenging the long-standing separation between Einstein's relativity and quantum mechanics. This could open the door to entirely new theories of quantum gravity, perhaps bringing us closer to understanding the true nature of space, time, and the universe's origins.
Non-standard inflation and its gravitational imprint. The theory of cosmic inflation helps explain why the universe looks so uniform on large scales, why distant regions have similar temperatures, and why space appears nearly flat instead of curved. But what if inflation didn't happen exactly as we think? What if there were variations, non-standard forms of inflation, that left behind subtle but detectable imprints?
One alternative is the idea of multi-field inflation. Instead of just one field driving inflation, multiple interacting fields could have shaped the expansion. In this scenario, different fields could have influenced space-time in different ways, leading to variations in how gravitational waves formed. Some of these waves might have been stronger or weaker than expected, while others could have distinct polarization patterns.
Another possibility is intermittent or staggered inflation, where inflation did not happen in one smooth burst, but instead started, stopped, and restarted in a series of phases. This kind of stop-and-go expansion could have created unexpected distortions in gravitational waves, introducing irregularities in their frequency or amplitude. Instead of a single continuous spectrum of primordial waves, scientists might see gaps, peaks, or other anomalies that don't fit within standard models.
Some non-standard models even suggest that inflation might not have been purely an expanding process. In aperiodic inflation, inspired by string theory and higher dimensional physics, the universe might have gone through a contracting phase before inflation kicked in. In this scenario, the Big Bang wasn't the true beginning, but rather a transition from a previous state of contraction to a rapid expansion.
The idea of warm inflation challenges another fundamental assumption about how inflation worked. In the standard model, inflation occurred in a cold, empty vacuum with almost no particles present until the expansion slowed down and energy was released. But in warm inflation, the inflation field continuously interacted with other particles during the expansion.
Even if current observations do not yet show clear signs of non-standard inflation, our ability to detect faint signals continues to improve. The possibility that inflation was more complex than we assume remains open, and future observations might reveal the full story of how the universe's first moments shaped everything that followed.
Cosmic phase transitions. Imprints on gravitational and CMB data. In the earliest moments of the universe, matter and energy existed in an extreme state, vastly different from what we observe today. The universe was hot, dense, and rapidly expanding, undergoing dramatic shifts in its fundamental structure. These shifts, known as cosmic phase transitions, were moments when the nature of particles and forces changed, much like how water turns into ice when the temperature drops.
One of the most significant phase transitions is thought to have occurred when the fundamental forces of nature separated. In the first fraction of a second after the Big Bang, all the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. As the universe expanded and cooled, these forces began to split apart, first gravity, then the strong nuclear force, followed by the weak and electromagnetic forces.
These transitions were not smooth or gradual. They happened in bursts. where the universe's structure changed suddenly. One of the most intriguing phase transitions relates to the Higgs field, which gives particles their mass. In the early universe, the Higgs field likely existed in a different state. As the universe cooled, the Higgs field underwent a transformation, settling into its current form and allowing particles like electrons and quarks to gain mass.
If this transition was abrupt, it could have generated powerful shock waves that disturbed space-time itself. If more gradual, it could have left behind remnants, bubbles of different physical states that merged together. These bubbles could have produced gravitational waves as they expanded and collided, potentially leaving an imprint on today's observable universe.
Some theories propose that our universe may have started in a higher dimensional state and then transitioned into the four-dimensional space-time we experience. Others suggest that what we perceive as dark energy could be the result of a phase transition that is still unfolding. Next-generation pulsar timing arrays may be able to detect faint signals from the early universe. If successful, these observations could reveal whether the phase transitions happened as expected or whether something unexpected took place in the early moments of cosmic history.
Topological transitions beyond traditional cosmic geometry. Topology describes the way space is connected, its overall structure, rather than just the objects within it. It determines whether space extends infinitely in all directions, loops back on itself, or contains hidden dimensions beyond what we can see. The question of how the universe's topology evolved during its birth is an area of growing interest.
One key idea is that during the early moments after the Big Bang, the universe may have undergone sudden topological transitions, changes not just in what it contained, but in the shape and connectivity of space itself. These changes would be more fundamental than phase transitions. Instead, topological transitions would reshape the very fabric of space.
A useful way to think about topology is to compare it to different types of surfaces. A flat, infinite plane and a sphere may look similar in small regions, but they have very different overall structures. A two-dimensional being living on a sphere would eventually return to its starting point if it traveled far enough in one direction. The same could be true for our universe. Space could be wrapped in a way that allows it to be finite yet without boundaries.
If the universe transitioned from one topological state to another early on, it could have permanently altered the way space is shaped on a cosmic scale. One possibility is that the universe once had extra dimensions that later shrank or became hidden. Some of these dimensions may have curled up or collapsed, leaving only the familiar three dimensions we experience today.
Another intriguing possibility is that the universe began with a more complex shape and later smoothed out into the structure we see today. Instead of expanding from a single point, space could have been highly connected, with multiple paths leading to the same location. If this were true, the large-scale geometry of the universe might not be as simple as it appears.
One approach to investigating this is to study the large-scale distribution of galaxies. If the universe underwent a topological transition, it might have influenced how galaxies formed, possibly creating unexpected alignments or symmetries in their arrangement. Future galaxy surveys with powerful telescopes could reveal whether these patterns exist.
There is also the question of whether topological transitions could still be happening. If the fabric of space can change its connectivity, then the structure of the universe might continue to evolve in ways we have yet to fully understand.